Good evening, all participants. I'm happy to invite you all for the day 3 of insights. I would like to invite Dr. C. Prabha, Head of the Department Mechanical Engineering, to deliver the welcome address.
Thank you, Professor Manoj. Good evening to all. On behalf of Department of Mechanical Engineering, Arjun College of Technology, I extend a warm welcome to this third day session of our 6 days online FDP program on machine learning applications in mechanical engineering trends and insights. I consider it as a privilege to welcome our esteemed chairman, Sri R. Suryanarayanan sir, Managing Trustee Engineer G. Srinivasan sir, Trustee Sri D. Raja sir, and our Secretary Dr. R. Suresh Kumar sir, and our beloved Principal Dr. N. Janahi Manohar sir for their continuous guidance and support in organizing this FDP. A special welcome to our resource person for today, Dr. Kartika, Associate Professor, Department of Computer Science and Engineering, Bannariamman Institute of Technology, Coimbatore. We are honored to have you with us to share your insights on how ML is transforming core mechanical domains like design, manufacturing, and predictive maintenance. I also welcome our dear faculty participants joining across the nation online over the next few days. This FTP aims to bridge traditional mechanical engineering with AI-driven tools to trends that are shaping the industry. I thank the organizing team for their dedicated efforts in making this program possible. Once again, a hearty welcome to all the participants, faculty members, organizers, and our institution faculty members. I hope this FTP will be an enriching and interactive learning experience. Thank you and welcome you all.
Thank you, ma'am. Now I invite Professor P. Moore to introduce our resource person.
Thank you, Manoj sir. Good evening, all. It is my privilege to introduce Dr. Kartika M., Associate Professor in the Department of Computer Science Engineering, Bannariamman Institute of Technology. Dr. Kartika ma'am brings with her over 15 years of rich teaching experience. She has completed her Master of Engineering from Kongu Engineering College and her Bachelor of Engineering from Bharat Niketan Engineering College. Her area of expertise include big data analytics, Internet of Things, data mining, deep learning, and wireless sensor network. She is also deeply engaged in emerging fields such as artificial intelligence and generative AI. Dr. Kartika ma'am has made significant contributions to research, having completed 45 journal publications. Her research work includes the development of VR skill enhancement tool for children with autism spectrum disorder and intellectual disabilities, showcasing her commitment to socially impactful innovations. She has successfully guided PhD scholars and has filed patent for her research work. In addition that, she has delivered several guest lectures and has authored 17 books in the field of engineering. She is also a lifetime member of the Indian Society for Technical Education. Let us warmly welcome Dr. Kartika ma'am. Now the session is yours, ma'am. Thank you.
Thank you, sir. Thank you, Vinit, sir, and thank you, HOD ma'am, for giving me this opportunity. Am I audible?
Yes, ma'am. Yes, ma'am.
Yeah, ma'am. Yes, ma'am.
Okay. Let me share my screen, sir. Okay. I hope my screen is visible.
Yes, ma'am. Visible, ma'am.
Yeah.
So once again, good evening, everyone, and a very thankful introduction. I'm truly delighted to be here as part of this FDP program. So the topic that I'm going to take is a very exciting topic. That is, we are going to explore how machine learning is reshaping the entire field of mechanical engineering. So how we can use machine learning in mechanical engineering. So now I know what some of you might be thinking. So ML, machine learning belongs to a computer science thing. So what does it have to do with my field, that is with my turbines, with my FEM? simulations or with my manufacturing floor? What ML is going to do? So that's exactly the question I am going to answer today. So by the end of the session, I want you walking out with a clear understanding of not just what ML does in your never domain, but why it matters, where it is already being used in industry, and how you can start applying it in your teaching and research. So that's what you can grasp at the end of this session. So we'll go through some real application areas. We will try to look at some case studies from the industry, and we will try to understand some fundamental ML concepts, and then cap it all off with a live demo where we actually build and run an ML model together. So that's what I have planned for today's session. So it's going to be a hands-on and practical session. So before going into the demo, so let us start with a question. So let me start with a question. How many of you have worked with sensor data from a machine? Or how many of you have run a finite element simulation that took some hours to complete? How many of you have did this? Have any one of you worked with sensor data?
Yes. Work on sensor data.
Okay. So by using datas, since on Professor have told that he has worked with sensor data. So from using the datas, we can extract the powerful insights from the data. That is, for example, we can predict when a machine will fail, or we can get you might have run some simulation results for hours. So instead of running it for hours, you can run it in milliseconds. That is exactly what machine learning brings to us. So what I'm trying to say means we are living in a great paradigm shift. So traditional engineering usually relies on physical equations and human intuitions. So humans will try to predict what is going on. That is traditional engineering. But nowadays we are living in the data-driven world. So data-driven engineering, it adds a third layer to our traditional engineering, that is learning from patterns in the data. So this is not just academic, okay? So industries like automotive industries, aerospace industries, and manufacturing industries are already deployed these systems, deployed this data-driven systems in their industries. So the three pillars that we have taken here are, first is data-driven decisions. So data-driven decisions, so instead of a human analyst manually reading the sensor data, ML models will continuously try to scan the data, or it try to scan thousands of signals, and it flag the anomalies in the data within seconds. So that is data-driven decisions. The second is speed and scale. So ML models, that is machine learning models, helps you to explore design spaces that is impossible for the human to evaluate. So third is smart systems.
One more question. Can I ask?
Yes, sir.
Okay. Well, going for machine learning, but what kind of software we are using that machine learning? Let me know.
Software,
yeah,
lot of open source softwares are there.
Yeah.
So the common programming language that we use for machine learning is Python.
What kind of application we can build for machine learning? Well, we are having two things to go on. One is when you go for hardware implementation, depends on hardware implementation. From the hardware, we have to simulate with the machine learning concept.
Yes,
Second
sir.
one is we are using for creating an app. they are using for a Python programming. From the database machine learning. From there, we are using for a machine learning concept. The two things we can use. Am I right?
Yes, sir. Yes,
Okay.
you're right.
Okay.
So next, the third is machine learning. This data-driven transformation will provide you smarter systems. Smarter systems means when you combine machine learning with the real-time data, you get the systems that don't just respond to failures, but it will prevent them entirely. So that shift from reactive to proactive is the heart of the data-driven transformation. I hope you understand the importance of data-driven transformation. Next, let us explore the major key application areas where ML is used in your mechanical engineering field. So the major areas where ML make concrete impact in mechanical engineering or these 6 fields. See this, this is all these 6 are a menu of opportunities for you. Okay, so the first and arguably most mature application is predictive maintenance. So predictive maintenance, it highly uses sensor data to forecast the equipment failures before they happen. We will dig deep into this predictive maintenance in our upcoming field. So predictive maintenance is using sensor data, we will forecast the failures. Next is structural analysis. Structural analysis is the next big application area. So here the models, that is surrogate models that are trained on FEM. FEM, you might know, finite element method. So that is trained on FEM. Those results can predict the stress fields in milliseconds. Okay, so usually the FEM simulations will run for hours. So if we use ML, we can predict it in milliseconds. Then we have thermal systems. So thermal systems here, ML models can learn complex thermomechanical behavior that is very extremely difficult to model analytically. So there also we can use ML. Next coming is fluid dynamics. So fluid dynamics is also another exciting area that is CFD. CFD is computational fluid dynamics. You might have know what is mean by CFD. So CFD simulations are usually notoriously expensive computationally. But when ML is used, that help us to dramatically cut the cost. Next biggest application area is quality control. Here we will mostly depend on computer vision based concept. Computer vision means image and video based analysis. So here cameras and neural networks on production lines will catch the defects that human inspectors would miss. That is done by the cameras. So that comes under the application of quality control. And finally, process optimization. So process optimization, it is continuously tuning the manufacturing parameters like some pressure, injection pressure, or some temperature, or some speed. We will try to tune it, right? We will try to tune it to maximize the output quality in real time. Okay, so that is what done in process optimization. So these 6 areas together span the entire product life cycle from design and simulation through manufacturing all the way. Sorry, I have moved to the next slides. So design and manufacturing to improve the quality. Okay, so this is the breadth of the application areas what ML cover in your mechanical engineering domain. Next, predictive maintenance. Now let's zoom into predictive maintenance because this is the application that's delivering the most immediate and measurable ROI in industry right now. So right now, a lot of industries are using this predictive maintenance only. predictive maintenance starts with the data collection part. So data collection here, for data collections, we will use sensors. So sensors for why? For measuring the vibration of the machines, for measuring the temperature of the machine, or for measuring the acoustic emissions, or for measuring the pressure. So these sensors are attached to the machinery. It will be attached to the critical machinery. So from there, raw data tries to stream continuously. The data streaming volume is at thousands. That is, we will stream it at thousands of samples per second. So if you take vibration part alone, for vibration alone, lot of data will be streaming. So what ML will do means, ML model sits downstream. It sits and it consumes this thousands of samples. That is streaming continuously live. The ML model sits downstream and consumes the stream. After consuming the live data, it will do two key jobs. First job is anomaly detection. Okay, so anomaly detection is what? Anomaly detection is nothing but it will try to spot the patterns that deviate from normal healthy operation. So for a normal healthy operation, certain types of patterns will be there. If the healthy operation deviates, then the patterns would differ. So this work is done by the ML. It tries to detect the anomalies. Then next what it will do means, it will try to estimate the life. What I mean is, for example, after detecting the anomaly, our ML algorithm will suggest us that this bearing has approximately only 200 operating hours left. So before that, it needs to be replaced. So like that, it will provide us the estimation, life estimation of the machines also. So this is the two jobs, major jobs ML algorithm will do. One, anomaly detection. Next, life estimation. So when the model detects something, immediately it triggers an alert. After getting an alert, our maintenance team, in industry maintenance team will be there. So maintenance team will then schedule a service window proactively. Okay, that is proactively means it it is planned during downtime, not during a critical production runtime. So if we undergo a maintenance in the production runtime, then there would be a lot of it will cost high. Okay, so usually the maintenance team will try to schedule a service in a downtime hours only. So this is what the complete predictive maintenance. So first data will be collected, then MN model will predict, then finally it will alert. So this is how a predictive maintenance will work in an industry. So next, let us get a bit more technical and let us look at what ML is doing in these three core engineering disciplines. That is structure analysis, thermal systems, and fluid dynamics. So each of these systems has its own challenges, and ML is going to address them in fascinating ways. Okay, so first let us consider about structural analysis. So the bottleneck here is here we will do some FEM simulations, finite element simulations. So they are accurate. You are in your discipline, you know what kind of structural analysis you will do. So we'll do with FEM type of analysis that is accurate only. But the only drawback here is that FEM analysis is very slow. Sometimes it takes hours, or it may take even days for complex models. So if we trained models on FEM results, and we can replicate those predictions in milliseconds by using ML. Okay, so more interestingly for this tasks and all, we will use a particular machine learning model called physics informed neural networks, PINs. Physics informed neural networks, PINs. So what this physics informed neural networks means, it will try to embed the it will try to embed the equations of your elasticity based, that is for structural analysis, what are the stuffs you will use. So that kinds of equations are embedded into the learning process. Okay, so this means that they stay physically consistent even when the training data is very less. Okay, so the previous literature surveys have shown up that there is a nearly 40% of improvement is there in damage localization for structural health monitoring by using this PIN, that is physics informed neural networks. So next, coming to thermal systems. So in thermal systems, we can use models like random forest or neural network. So these are used to predict the temperature and pressure distributions in components like clutches, brakes. So where thermomechanical process are there. So in that areas, we can use this machine learning algorithms like random forest and neural networks. So here also we can use PINs, that is physics informed neural network. So this will greatly outperform purely data driven models. Okay, so why PINs is very better means, since it is directly involving physics based learning, it acts as a very powerful regulator. That's why compared to other machine learning models, if we use PINs, the accuracy is greater. Next is fluid dynamics. So fluid dynamics here, ML models are replacing the expensive, as I told before, it is replacing the expensive CFD runs. So instead of rerunning a full CFD simulation for every iteration, so the ML model will predict the efficient, that is drag efficient, instantly. So this is enabling some rapid exploration in design spaces where which was previously very expensive. Now by using ML model, we can easily predict it. So the applications, these engineering, a lot of applications are there with these core engineering disciplines. So you can use ML models in all these core engineering disciplines. So before we go further, I want everyone to make sure clear on a fundamental distinction in ML, that is which determines which algorithm you should reach or which algorithm you should use for a particular problem. Okay, so the distinction is between classification and regression. First, you need to understand where I need to use classification, where I need to use regression. Okay, simply saying, classification answers the question, which category does this belong to? Okay, which category does this belong to? So how the answer would be? The answer would be a discrete label, discrete one, faulty or not faulty, pass or fail, whether it is a type A or type B. So that would be the answer. So in those criterias, you can go for classification algorithms. For example, in mechanical engineering domain, let me say that you are going for a fault diagnosis. Fault diagnosis. For that, you have given some vibration data. What kind of output you would expect from this data? Is this machine is this machine experiencing imbalance, or is this machine experiencing some misalignment, or whether the bearing has failed? So these are the things that you will try to diagnose in fault during fault diagnosis model. Or if you take for quality control, what kind of output you might expect? Is this manufactured part defective or acceptable? Right? Defective or acceptable? These are the two outputs that we would expect. You would expect either one, defective or acceptable. Okay, so the this is in those applications we have to use classification. So the algorithms that handle these problems are logistic regression, support vector machine, decision tree, random forest. So these are the basic algorithms. Lot of other classification algorithms are also there. So let me just touch the basic algorithms alone. Okay. So in our demo, we are going to see about classification only. So next, regression. So regression, on the other hand, it answers like how much, how long. Okay, how much, how long. So what would be the output? The output is a continuous number. For example, what is the remaining useful life in hours? What is the stress in megapascals? What is the temperature in degrees Celsius? Okay, so the output would be a continuous number. For example, if you want to predict how many more operating hours a bearing has before failure. So how many operating hours are left for a bearing to fail? For this kinds of job, we can use regression. Another example, if you want to predict the power output of a wind turbine as a function of wind speed, then we can go for regression. Okay, so if you want to predict the power output of a wind turbine as a function of wind speed, we can go for regression. Okay, so keeping this distinction clear in your mind, it will help you frame which ML problem you have to start with. Okay, so most real engineering problem can cast as either one only, and choosing correct algorithm will make a huge difference in your model performance and interpretability. For regression task, if you choose classification algorithm, then it would be a great degradation in your performance. So you need to understand for which problem I need to choose which kind of algorithm. Most of the problem comes under this two domains only, two broader domains only, classification and regression. Next, let us talk about what's happening at the cutting edge. That is the technology trends that are changing and amplifying in the engineering domain. The first is IoT, Internet of Things. So smart factories today are bristling with sensors. So every machine, every conveyor, every actuator is generalizing or it's generating the data. So this continuous real-time data stream is the lifeblood of our ML models in industrial settings. Okay, so without IoT, we have no data to learn from the industries. So IoT will help us to generate real-time data from the machines. Next big concept is digital twin. You might have heard this name, digital twin. So digital twin is nothing but it is like a living replica of a physical asset. Living replica of a physical asset that is updated in real time with sensor data. Okay, it's like what to say, you can run what if scenarios on the twin without touching the physical machine. Okay, we can simulate the effect of a parameter change, or we can simulate and see if a temperature increases this much level, what would be the occurrence of a machine. So everything you can simulate and see. We can predict the end of the life of the machinery also. Okay, so this is one of the incredibly powerful thing for life cycle management and risk assessment, digital twin. Next is physics informed ML, that is PIML. Already we have seen PIN, physics informed neural networks, right? So that comes under PIML only, physics informed ML. So it is one of the biggest deep learning models in engineering domain. So this is like a black box with no physical grounding and all. So PIML, as the name informed, it embeds physical laws, Newton's laws, conservation of energy, elasticity equations, all are embedded directly as constraints in the learning process. Okay, so this gives you models that are both data efficient and also physically interpretable. Okay, that is physics informed ML. This is some hybrid approach. Okay. So finally, Edge AI and federated learning. So Edge AI and the federated learning helps to solve the deployment problem. So instead of streaming all sensor data, usually sensors will be present in the machinery, and that data has to be collected by means of some IoT sectors, and it has to be brought to some cloud, and their processing will be done, and again the output will be shifted to the machinery, or output will be shifted to some maintenance team, right? This is the process. So instead of streaming all the sensor data to a central cloud for processing, Edge AI helps us to run the model, ML model, right on the machine itself, or right on the gateway device itself. Why we have to run in the gateway device, or why we have to run on the machine itself? Because it helps us to reduce the latency and bandwidth. Okay, so that is the usefulness of Edge AI. Next, let us see what is meant by federated learning. So federated learning, it allows the models to be trained collaboratively across multiple factories or assets without sharing their sensitive raw data. So each own factory can run their models. Okay, so this is called as federative learning. So federated learning greatly helps us in maintaining the privacy of our own data. Okay, so these trends together, that is IoT, digital twins, PIML, Edge AI, and federated learning, are moving our ML from research labs into factory flows in a very real time. Next, let us see about some real world case studies where actual deployments of ML has made. Okay, so the first where ML has made is in plastic injection modeling. Sorry, not modeling, molding. Plastic injection molding. So this is one of the highest volume manufacturing process in the world. So the challenge here is that quality defects. Okay. Here ML models have collaborated with or correlated with lot of parameters to check the quality in real time, and it will automatically adjust the settings before defect can occur. So this ML integration has reduced the scrap rates, and it improved the consistency significantly in plastic injection molding industries. Then second is air compressor maintenance, air compressor predictive maintenance correctly. So in industrial air compressors, it has some critical infrastructure. They need a lot of pneumatic systems throughout the plant. So ML model that are trained on pressure, temperature, and vibration data from these compressors will predict the component failures, and it will enable the maintenance aligned with the industry 4.0 goal, that is making zero unplanned failures. Next, the third case study is wet clutch thermomechanics. It is an automotive engineering problem. So, what to say? That is, meta models trained on FEM simulation data can predict the temperature and pressure distribution, including clutch systems during engagement. So this has replaced expensive and time-consuming full FEM runs, that dramatically speeding up the design iteration cycle. And finally, the origin of the digital twin concept itself, that is NASA. So NASA has been running virtual simulators of spacecraft since 1960s, first to support Apollo missions. Okay, so these weren't called digital twins at that time, but that's exactly what they are. So the concept has since been commercialized and is now a standard practice in aerospace, and it is increasingly used in industrial equipment also. So I want to be honest with you, ML in engineering is powerful, but it is not without challenges. So we have to understand the challenges, especially for those of you who will be guiding the students or collaborating with the industries on ML projects. We need to understand the challenges. The most persistent challenge in mechanical engineering domain is data scarcity. Data scarcity. So real failure events are rare by design. So in a well-maintained plant, machines don't fall often, isn't it? This means building a robust failure detection model require either long data collection period or very clever use of some synthetic data and transfer learning. Okay, because usually we don't have that failure model data. That's what I'm trying to say. Next, another thing is clean labeled data sets are very expensive to produce because labeling each data requires expert domain knowledge. If this happens, this is a failure. If that happens, this is a failure. So for that, expert domain knowledge has to be there, so that only labeling of the data is very expensive. Next, legacy system integration. So legacy system integration is a significant friction point in practice. For example, many manufacturing facilities run equipments that is 10 years, 20 years, or even 30 years old, isn't it? So retrofitting these machines with sensors and connecting them to modern data infrastructure, it involves both technical challenges and organizational resistance. Okay, so these are the current challenges. Okay, the skill gap is real. Good ML engineering in mechanical engineering domain require people who understand both mechanical systems and data science domains deeply. So this is actually a tremendous opportunity for the next generation of engineers that you are training. Then coming to model interpretability. So model interpretability remains a concern, especially for safety critical applications. For example, a black box neural network will say, this system will fail in 50 hours. But it is hard to trust because you can't understand why it made that prediction. So this is driving significant research interest towards explainable AI. So explainable AI in your domain, it is called as physics informed ML. So if a system has, if it has predicted a system will fail in 50 hours, it has to say by these things only, by these parameters only, I am telling that the system will fail in 50 hours. The reason will be driven back by using explainable AI or physics informed ML. So looking forward, our hybrid PIML, physics informed ML models, deeper IoT integration, and democratized tools with natural language interfaces and broader industry 5.0 of sustainable human-centric and some smart manufacturing. So these are the directions the field is moving toward. These are the future directions and the opportunities for both research and teaching in this domain. So let's bring together, before we dive into the live demo, the first key takeaway is that YAML is not a research prototype anymore. So predictive maintenance, structural health monitoring, and process optimization are live in today's industry. So delivering measurable returns. So this is a production ready technology. Second one is choosing the right ML task matters enormously. So if your problem is what type of fault is this, then that is a classification problem. Okay. So if your problem is like how much life does this component have left, that is a regression problem. Okay. So getting this framing right at the start itself will set up you for greater success. Then the third is future of ML in engineering is hybrid. That is, physics informed ML model has to be combined with IoT data streams and edge AI deployment. That's why I'm saying it is a hybrid thing. So combination will give you models that are very accurate, very interpretable, and deployable in real world industry environments. Okay, so this is what I tried to cover in our PPT. Now let me take a short demo. We are going to take a real data sets on equipment failure, and we are going to check how a classification model works better. Can we see the real demo? Let me share my screen. I hope the screen is visible to you all.
Yes, ma'am, it's visible, ma'am.
Okay. So I'm running, for easy task, I'm running it in Google Colab. Okay, I hope you might have heard the word Google Colab.
I think what kind of software is it?
It is Google Colab.
Okay, okay.
Google Colab, collaboratory.
Okay, fine.
So this is an online IDE that is released by Google. Okay, you can directly go to Google and give Google Colab, and here Google Colab notebook will display. You can just click on it. New notebook. You can give new notebook, and like this notebook will be opened. So this is an online IDE. For doing basic things, basic learning purposes, you can use Google Colab. How you can use means you can connect with you. If you click connect button, here a connect button is there. No, if you click connect button, it will connect with your drive, with your Google Drive, Gmail Drive. It will get connected. Okay, and you can rename this file. Rename it as sample. So the extension of this file is .itynd. Okay, for normal Python file, the extension will be .py.
.py.
Yes, for Google Colab file, it will be .itynd. Okay, so you can download and keep also. You can download and keep this file also. So all this will be saved in your drive. If you go to your drive, after signing into your drive and connecting with your drive, if you go to your drive and check, you can check a file. Sorry, a folder in the name Colab notebooks will be created. A folder in the name Colab notebooks will be created. Here, whatever files you are working in Google Colab, everything will be saved. See here, all are IPONB files, right? So these are the files that have been saved through Google Colab. I hope you can now understand how to work with Google Colab. And in Google Colab, two parts are there, code part and text part. This is the code part. So simply you can type your code, and for execution, you can click this run button. Okay, you can click this run button, or else some shortcuts are there. You can click Control Enter. If you click Shift Enter, after executing, a new tab will be opened. Okay, so two shortcut keys are there, Control Enter and Shift Enter. Then text part. So text part, this is used for documentation purpose. This is my sample program. So this is for documentation purpose. Okay. So these are the two things. This Google Colab completely resembles our Jupyter notebook. So a special ID is there from Python. That is instead of working with Python IDE, we can use Jupyter notebook. You might have heard this word Jupyter, Jupyter, Jupyter notebook. So that this Colab completely resembles that IDE. It's similar to Jupyter notebook. Okay, so Jupyter notebook works. We can work offline. For working with Google Colab, we need internet facility. That is the difference. And in the right hand side, you might seen some icons. So if you click this icon, this is where we can upload our data. This is where we can upload our data. See, these are some sample data. If you want to upload new data, you can click this upload button and you can upload the data from your computer. So the one drawback of Google Colab is that once you close this tab, the data that have been uploaded will get lost. Okay, this is like a RAM memory. Once you are using it, you can use the data. Once the internet connection goes off, or once you turn off this, you close this tab, the data that is uploaded will get lost. Once again, you have to upload the data. Okay, that is the drawback of Google Colab since it is
Okay, I have one doubt.
Yes, yes.
Yeah,
Sir.
you cannot. You can upload to GitHub and then draw data, and then you have to use for merge, that kind of root branches that we cannot able to do. Once you are done with the
For
program and-
cloning,
Yeah,
for
yeah.
cloning with the GitHub, we cannot do in Google Colab. You can just take the py file and you can work in Google Colab. For cloning,
What CSV file we have, Visual Studio, JavaScript. From that we have from raw data, you can save that file and then you can build the data into the I think
yes, sir. You can just download the raw data and you can convert it as a CSV file and you can upload it in Google Colab and use.
Okay.
But direct cloning of GitHub into the Google Colab is not that much efficient. If you use other IDs,
this is for a sample practice demo, just for a reading, just for a minimum requirement of doing for a Google Colab. Am I right?
Yes, sir. Yes,
Yeah.
for learning purpose, you can go for Google Colab.
Okay.
Okay. For doing a complete project, this is not sufficient. You have to go for the ID like VS Code or PyCharm is there or Anaconda is there. So you have to go
ID is integrate development environment Eclipse. I mean that we can go for a Java code. That will be more, right?
Yes,
Yeah,
not
yeah.
Java code, not Java code specifically. Java code is used for developing the front end stuffs.
Yeah, front end, back
For
end.
the complete development of the project, you can use VS Code, Visual Studio Code. That package you can use.
Visual Studio Code. SQL Server Management Studio.
Yes. Then the data sets, you can download the data sets from Google. UCI machine learning repository is there. This is a open source repository. Another biggest repository is like us sir told, lot of data is available from GitHub. GitHub.com, you can just download the data set and use. Another biggest repository is Kaggle. Kaggle is the biggest repository of data sets. There you can download the data set. Okay, you can download the data set and you can upload in your Google Colab and you can use. Okay, so like that only I have downloaded a data set, that is your equipment failure data set I have downloaded. So these are the basic packages that we need to install. If I want to make you understand each and every word, I can't complete it within an hour. So these are the basic libraries that you need to import for doing any machine learning stuffs. NumPy, Pandas. So NumPy is for doing numerical calculation. Pandas is for doing a data manipulation task. And matplotlib.pyplot and Seaborn is used for visualization, for graphs, for generating graphs and charts. We will use matplotlib and Seaborn. And sklearn.model. Sklearn is the biggest library where all machine learning related algorithms are present. Okay. For example, if you want to do some classification algorithm, it is present in sklearn only. Okay, so my sklearn.model.selection import train test split. So train test split and cross validation score I have imported. So what is train test split means? Data will be as a whole. Okay, it will be of 1,000 records or 1,500 records. So we can't use the complete data for training. We need some data for testing. We need some data for validation. So splitting our data automatically, we use this package, train test split. Okay. And cross validation is also used for splitting our data. So usually we will use 80:20 rule. That is 80% of the data is used for training and 20% of the data is used for testing. Cross validation score is nothing but here we will set some k values. K value is like we will for example, if you take k equal to 5 means our data will be split into 5 junctions. So in that 5 junctions, 5 iterations it will be executed. In the first iteration, first part of the junction is considered as test data. The remaining 4 parts will be considered as training data. And in the second iteration, the second junk will be considered as a testing data. 1, 3, 4, and 5 will be considered as a training data. So that is called as cross validation. Okay. Then label encoder and standard scaler is there. Label encoder is used for converting the categorical data, text data into numerical form. So all the machine learning algorithms will understand only numerical data. It won't understand any categorical data, any text form of data. All this data has to be converted into a numerical form. So for converting, we will use label encoder. And standard scaler is for normalizing the data. Okay. Then these are accuracy score, classification report, confusion matrix, ROC score. These are the metrics that is used for measuring the performance of our model. Okay. Next, we are going to import the random forest classifier. This is one of the classification algorithm. Gradient boosting classifier and logistic regression. SVC is support vector machine decision tree classifier. I am going to import 5 algorithms for training my model. Okay. So next is auto download. Here I have just used this UCI machine learning repository. So this is the URL from where I can download the data set. So I am simply giving the URL here and I am calling a function called auto download data set. So this data set will automatically download our data. Next is loading and exploring the data set. So after downloading the data set, I am storing the data set in my data frame name DF. So next I am just printing and seeing shape. What is the shape? How many rows and columns are there in my data set? Then head, it will give the first 5 rows. And df.daytypes, it will tell us what type of column each is. Whether it is a number or whether it is a string or whether it is text, it will try to tell what kind of column. Then here I am using value counts. So this is like how many, here we are having a column called machine failure. So in that, how many are healthy, how many are failed. For counting that, I am using this function. Next, df.describe. So this is used for calculating the mean, median, standard deviation, minimum value and maximum value in our data set. Okay, so this is the output you can see. So this is our data set. First 5 rows, UDI, product ID, type, air temperature, process temperature, rotational speed, torque, tool wear, machine failure. Then some HDF, PWF, OFF, RNF. These I don't know what are these. So these are the data set columns. So among this, I have just checked what are the data types: integer, object, float. Okay. So next is distribution. If you take the minimum value is 1 and the maximum value is 10,000. And machine failure, there are 9,661 values with failure and 339 values with not failure. Okay. So I have also drawn the graph. How many are failure, how many are not failure. And also I have checked the correlation. What is the relationship between each and every variable? What is the relationship between air temperature and process temperature? What is the relationship between rotational speed and air temperature? I am checking the correlation. This is feature correlation matrix output. So next step is feature engineering. So feature engineering is the second. After downloading the data, you will just explore and see what is there in the data. After exploring what is there in the data, you have to do feature engineering. Feature engineering is like, what are the things that I need to consider for my model training? What are the things that I should not consider? What are the things I should leave it? So that comes under feature engineering. Okay. So here, if we take in our data set, the useless columns are UDI, product ID, TWF, THTF, PWF, OSF, RNF, all these are useless column. They have no pattern for predicting the failure. So simply I'm dropping it. Next is we are trying to encode the type column. So in type column, if you check here in our data set, in the type column, just a minute. Type is of what? M, L, L, L. So these are what? These are some text data, right? String data. So this has to be converted into numerical format. That's what we are going to do. I'm going to convert that type column into numerical data. For that, I'm using label encoder. So what label encoder will do means it will try to convert the categories into numbers. For example, the type is of names M, L, C. It may be of any type. Okay. So let us take two types, M and L. Okay. So alphabetically, L comes before M, right? L comes before M alphabetically. So what label encoder will do means it will just mark 0 for L and 1 for M. Okay. So what I am trying to say is categorically it will arrange it in the ascending order, in the alphabetical order, and alphabetically it will give 0, 1, 2, 3, 4. So that is what label encoder does. Okay. Next is we are finding the difference between process temperature and air temperature, and we are also trying to power some feature. What is the difference? What is the torque? What is the power approximation? So all we are doing it, and we are finding out our target is machine failure. This is what I'm going to find. So what I'm going to do means I'm going to drop that machine failure alone, and I'm going to save this machine failure column into Y, and remaining all will comes under X. So by using X, I'm going to find Y. Okay. So X is our features and Y is our target. Okay. So based on X and Y, I'm going to split the data, train data, test data, Y train and Y test. Okay. After that, I'm going to normalize it. Okay. So this is our feature. So features are type, air temperature, process temperature, rotational speed, torque, tool wear, temperature difference, and power approximation. So by using this, I'm going to find what? I'm going to find the machine failure. Okay, so total training is 8,000 samples and total testing is 2,000 samples. So altogether, how many samples are there in our data set? 10,000 samples are there in our data set. So next we are going to train our classifier. So simply you can call the models, logistic regression, decision tree, gradient 4. I will share this demo. You can run it and see. Okay. Random forest, gradient boosting, and SVM DBF. I'm just going to call all the models. So these are the these are the parameters that I need to pass for each and every model. So I'm passing it. Next, I'm training the model for all logistic regression, SVM. For all, I am training it. Then I am predicting it also. Finally, I am finding out the accuracy. So this is the accuracy. For logistic regression, I am getting 96.85, decision tree 98, random forest 98, gradient boosting 99, SVM 97. Like this only you have to train multiple classifiers. Simply you can call the name. So if you want to train with a particular algorithm name, you just ask the code for ChatGPT or in Google, you can ask for the code. In Colab itself, we can get suggestions from Google. Okay. Agent will be there for helping us to code. Okay. You can just take that code and execute and see how it is working. Download the dataset and execute and see for any kind of machine learning models. After that, we need to visualize and see which model is performing good. See here, we have got the results here. I'm just visualizing it by drawing some charts and graphs. I'm visualizing it. This is the code for drawing the charts. Okay. So when comparing these charts, which is greater, gradient boosting is greater. Okay. Then we are going to work with random forest. So random forest also I'm working it, and I'm generating what are the classification, what is the accuracy, what is the precision value, what is the recall value, and what are the features that are of most important. So if we see here in this bar chart, which feature is more important? Power approximation feature is more important. After that, torque is more important. After that, rotational speed is more important. After that, tool wear is important. After that, temperature difference is important. After that, air temperature and process temperature. Finally, only type. So by this feature importance, we can check which feature is very, very important for predicting our machine failure. So far we have used train test split function. Here I am using cross validation. I have already told what is mean by cross validation. So for every fold, the model is run. Okay. So for every fold, I am executing random forest algorithm. So fold 1, I am getting 95%, fold 2, 94%, fold 3, I am not getting any percentage, fold 4, I am getting 91, and fold 5, I am getting 95. So for fold 1 and fold 5, I am getting equal results. Okay, so this by this also we can just sample our data randomly, and we can execute and see how my model is performing. Okay, so I have covered some small learning of machine learning for predicting the machine failure in your mechanical engineering domain. So like this, you can also download any kind of data. Lot of data are available in Kaggle. You can download and you can work with machine learning, any machine. You can simply take a random forest or decision tree model. All the codes or everything are available in ChatGPT or any AI models or Google. It is available. You can execute and check how it is actually predicting the failures. Okay, this is a backend. And for this, if you create a front end, you can easily create a simulation model for your equipment failure. Okay, this is a backend code. For this backend, you can create a small front end model, and you can randomly the data will be collected from the IoT sensors, and the data will be displayed. And it when an anomaly is detected, directly it will give an alert. That front end part you can create it easily. Okay, so I hope you have got some knowledge of how a ML model works for your mechanical engineering domain. Is it clear? Is there any doubts? Professors, is there any doubts? So as I told, a lot of sites are available. Kaggle is there. USA machine learning repository is there. So first to start with ML algorithms. In Kaggle itself, you can learn how ML works. So in nowadays, nothing is needed. You just have to understand how to download the data and how a machine learning model works. That's enough. Coding, everything is available in ChatGPT itself, or in Gemini, or in Colab. If you check, a chat will be there. It help you to run through the complete code. You just execute and see how it is working for your mechanical engineering domain. After completing this ML based models, you can go for deep learning, vision based projects, identifying defects in the machinery parts. Lot of vision based models are also there. Then you can go for complex hybrid models like physics informed neural networks, the real interpretability, how you can make the real interpretability in your mechanical engineering domain. That you can go in the third way. Okay, so first you try with ML algorithms. So that's with my presentation.
Participants, any doubts? Participants, if you have any doubts, please clarify with our resource person. So
ML websites for basic learning Professor Naveen Kumar sir. So best ML websites for basic learning is in YouTube. Wait, let me share and show you. I hope my screen is visible.
Yes, ma'am. Visible, ma'am.
So before learning YAML, you need to understand statistics, that is basic concepts you need to know. I think it is very easy for you guys because you all are dealing with lot of equations and lot of things. So statistics and all might be very easy for you. So for learning the basic statistics of machine learning, you can use StatsQuest site. StatsQuest with Joe Starmer. So this is a very nice site for understanding the statistics behind the machine learning. That is the math behind machine learning. Because before knowing the concepts, we need to understand what is the math behind machine learning. So though it is a foreign YouTube channel, the understanding is very, very easy and all comes with simple stuffs only. So it would be very easy for you to learn the statistics behind machine learning. See here. Let me execute and show you. See, for everything, the complete caption will be there. Whatever he is saying, the complete caption will be there. And the watching criteria of this YouTube would be very interesting. So you try and see StatsQuest by Joe Starmer. This is for understanding the statistics behind machine learning. And if you want to really learn coding, you can go for code basics. This guy, this specs guy, code basics. He has taught the complete machine learning stuff. See, lot of machine learning, deep learning, statistics, everything is there. And his videos are also very small, not more than half an hour. Not more than half an hour. Half an hour is maximum time. It is only 15 to 20 minutes only. And in his videos, he has given the complete code. Everything is given by him. Complete code is there, data set, whatever data he has used, everything is available. So you can execute and see it live. Okay, so code basics is very, very easy way of learning machine learning. If you are not good in English, there are a lot of Tamil channels or there, Hindi channels are also there. But I have learned by these things only. Statistics by Joe Stormer and machine learning by using code basics only. Then LLM, a lot of things are there. You need to understand first machine learning. You have to start with machine learning, statistics, deep learning, then LLM optimization, transformers. Like this, you need to go. That's it. Is it clear, sir?
Yes, ma'am. Yes, ma'am. Anybody else? Participants?
Yes, clear. Okay.
Okay, fine. Now I invite Professor K.A. Anish, Department of Mechanical Engineering, to deliver the vote of thanks.
So good evening to all. Thank you for all the participants to be engaged with us into this third day of the session. Now I would like to express my gratitude to our chief speaker, Dr. Kartika ma'am, for sharing us with their presence and giving such a valuable thoughts with us. From my side and the team of our Department of Mechanical Engineering, ACT, gives a special thanks to you, ma'am. So your enthusiasm and involvement brought life to us to this gathering, about with a clear-cut knowledge about the source of machine learning code with various type of sectors like structural analysis, fluid dynamics and thermal system, etc. with a full-fledged concept, ma'am. Once again, I would like to thankful to all the participants, to your presence and your active involvement. So with this, I just conclude my vote of thanks. Thank you all.
Thank you, sir. Thank you all.
Thank you, ma'am. Thank you, ma'am. Shall we wind up the session now?
Yes, sir. Yes, sir.
Yes, ma'am.
Thank you, ma'am. Thank you, ma'am.
Thanks.
Participants, kindly fill the feedback form for the today's session. Participants, kindly fill the feedback form.
May I leave, sir?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Thank you.
Yes. Thank you, ma'am. Thanks a lot, ma'am.